Good morning, everybody. Today we are going to discuss this multiple pulse width modulation. In the previous class, already I have discussed the single pulse width modulation. So in single pulse width modulation, what happens? For one half cycle, uh, you are getting only one pulse, right? So that is nothing but single pulse width modulation. Now, in this class, we are discussing multiple pulse width modulation. So in this multiple pulse width modulation, for first half cycle, what happens? Two pulses, and the second half cycle, what happens? Two pulses, right? So that's why it is called as multiple pulse width modulation. The pulse width, the pulses may be increased. You can increase the pulses like 2, 3, 4, and so on like that. Whatever the pulses you require, you can generate those pulses. So this multiple pulse width modulation having some advantages and some drawbacks, right? So we'll discuss one by one. So here the number of pulses per half cycle is 2. That will indicate with n, right? So now what is the pulse width? Pulse width is 2d by n. So here also 2d by n, here also 2d by n, and here also 2d by n. So this is your pi and this is your 2 pi, right? So here if this is total 2d by n means this half part will be d by n, this half part will be d by n, right? Now here one parameter we have to define here, which is called as gamma. So as per the textbooks, what happens is, and gamma is defined like this. So gamma is defined as it is the angle difference between 0 and the middle of the first pulse. That is the important point we have to identify. And here, see, if I want to define this point, see this is, this total one is gamma. Whatever this first part is d by n. So what is this point is gamma minus d by n, right? Similarly, if you want to measure, if you want to find out the point here, what happens? This part is d by n. Therefore, what is this point? Gamma plus d by n, right? Similarly, for this pulse, what happens is pi by 2 plus this gamma minus d by n. And what about this point is pi by 2 plus gamma plus d by n. Like this for the negative half cycles also, right? Now we'll derive the RMS output voltage equation. What is the RMS output voltage? Vrms square is equal to 1 by pi integral 0 to pi Vs square d omega t. For RMS, the half cycle is sufficient, right? So now this Vrms square is equal to 1 by pi. What is the first pulse limits? Gamma minus d by n to gamma plus d by n. So this one, gamma minus d by n to gamma plus d by n, Vs square d omega t, plus second pulse. What is the second pulse duration? This point is, I said, I already discussed. What is this point is pi by 2 plus this part. Therefore, pi by 2 plus gamma minus d by n. So this one. And what about this one? Pi by 2 plus gamma plus d by n. Vs square d omega t. And if you simplify this one, finally what you will get? Vrms is equal to Vs into square root of 2d by pi. See, this output voltage equation is similar to that of your single pulse width modulation. See, Vs into square root of 2d by pi. So the output voltage equation is same as that of your single pulse width modulation, right? See here, because of n is equal to 2, just substitute here n is equal to 2, and finally we'll get this equation. Okay. So this is about your RMS output voltage equation, but as usual we have to find out the Bn component, because every time the An as well as A0 component is 0. So we have to find out the Bn component, right? So if you are going to find out the Bn component, what happens? We have to consider total cycle. One full cycle you have to consider. For each pulse, you have to find out the Fourier series. So now we'll discuss. So this one, Bn is equal to 2 by t integral 0 to t v of t sin omega t d omega t, right? So what is the time period for full cycle means? You have to consider 2 pi, right? What is the first pulse? See this first pulse, this is the first pulse. 1 second. Gamma minus d by n to gamma plus d by n. Second pulse, pi by 2 plus gamma minus d by n to pi by 2 plus gamma plus d by n. Third one is what happens? Pi plus this one, pi plus gamma minus d by n to pi plus gamma plus d by n. What is the third one? 3 pi by 2 plus gamma minus d by n to this point. This point is 3 pi by 2 plus gamma plus d by n. So each and every interval I have done this. And finally, if you simplify, what you will get? So this Bn is equal to minus 8Vs by n pi sine nd by 2 sine n pi by 2 cos n pi by 4 cos n of gamma plus 3 pi by 4. Okay. So this is V0n, and this component you will get, because if you substitute our general equation like a naught plus an cos n omega t plus bn sin n omega t, so because a naught and an are zeros, finally you have only bn component, so that's why you have used this one. And see, this equation is valid only for two pulses. If the pulse number is increases every time, you have to derive the equation. So this is one drawback in multiple pulse width modulation, we can say. Okay, right. Next one, the most important concept is this one, right? So in this, first of all, I want to use carrier wave to generate the pulse. This is the carrier wave. Okay, this is the reference wave. I have taken two references to define to give one important point. So two reference waves I have taken. Right. First, if you consider this is the reference wave. All right, this is a reference wave. For this reference wave, whenever this carrier wave is greater than this reference wave, you will get the pulse. Here also, whenever your carrier wave is greater than your reference wave, you will get the pulse. Next one, this one, right? Second pulse, second reference wave. Here also the same. Whenever your carrier wave is greater than this magnitude, VR2, then you will get the pulse. Right? Here also the same. Now, here, what is gamma? We have defined already. Gamma is nothing but it is the angle difference between your origin point to the first middle of the first pulse, right? So here, if you take this pulse, this is also same. So gamma is nothing but origin to the middle of the first pulse. Therefore, if you change the pulse width, your gamma will not change. That is a very, very important point. So in some textbooks, they have given one equation which is not that much good. So you just follow this one here. The reference, whenever your pulse width is changes, your gamma will not change. When your gamma will change means whenever you will change the reference, I mean carrier frequency, whenever you will change the carrier frequency, this triangular wave, then definitely your gamma will change. Otherwise, it won't be changed. Okay. Now here I am defining the number of pulses per half cycle NP is equal to FC by 2FR. How you are getting this equation? See, this is 0.01 means what happens? Pi. And that means 180 degrees. Here, what is this one? 0.005 means what happens? Pi by 2, 90 degrees. Right. So, the number of pulses per half cycle, how you are defining means, so for one full cycle, if you take, here I have taken only half cycle. If you take one full cycle, what happens? Positive half cycle, 2 pulses, negative half cycle, 2 pulses, totally 4 pulses, right? Then how can you generate this carrier frequency means to get 2 pulses per half cycle, definitely what happens, your carrier frequency will be different than that of reference frequency. Generally, what is your reference frequency is 50 hertz, right? Fundamental frequency, reference frequency, fundamental frequency is 50 hertz. Then whatever the carrier frequency means, that is different. That carrier frequency and reference frequency are different. So, but to get these pulses, what happens for to get 2 pulses per half cycle, definitely this carrier frequency will be 200 hertz. Then only it is possible. Otherwise, it won't be possible. Understand what I am saying? So now what is this? The number of pulses per half cycle is FC by 2FR, right? Half cycle. What is FC? Is nothing but 200 hertz. FC is nothing but 200 hertz. Then 2 divided by 2 into FR. What is FR? 50 hertz. Therefore, 200 divided by 100 is 2. So this is the formula for number of pulses per half cycle, right? Depends upon the general formula, depends upon the pulses you require. So what is the carrier frequency, right? So if you are using only one carrier wave per half cycle means only one pulse will generate. So to get 2 pulses means what happens? This is different. That means the carrier wave will be 2 times it will be repeated. So that means what the frequency is 200 hertz. So that is the carrier frequency. Understand what I am saying, right? Next, coming to what we are taking here, one more important concept is this one. So here I have taken only one reference wave. I'm not using multiple reference waves. So here the first thing is this is pi, 0.01 means 180 degrees. This is pi by 2 means 0.005. Right. Now here I said whenever your triangular wave is greater than your reference wave, then you will get some pulse. Here also the same. Now this is called as pulse width. We already discussed 2d by n. Right. Now what is C? This total one 0 to 0.005 means how much? 90 degrees, which is nothing but pi by 2. This, how can I write? Pi by 2 is nothing but what happens? Pi by n, because n is nothing but number of pulses. Right. Next, coming to here, this one, pi by 4. I mean, this half part. Half part means what happens? 45 degrees. This is 90 degrees from 0 to this pi by 2 means 90 degrees. From 0 to this middle point exactly, what is this one? Pi by 4, which is nothing but 45 degrees. So that I have written here. So which is nothing but, how can I write? Pi by 2n. So where n is nothing but number of pulses. Next, this one. This is nothing but non-conduction period of your switches. Here also, non-conducting period of switches. See, whenever switch is conducting means some output voltage is presented in full bridge inverter. Here, nothing is conducting means what happens here? Your output voltage is 0. So if you take output voltage is, I mean, if you take here this point, non-conduction period, that is defined with X. Here also, the device is not conducting, so that is also we can define with X. Understand? And you already know this gamma. What is gamma? It's it is defined as origin to the middle of the first pulse, right? So now therefore this gamma will be equal to this pi by 2n. Understand what I am saying, right? So gamma, how can you define, which is nothing but pi by 2n. We can also write like this, right? Next thing is we have to find out this x value and direct pulse width. We have to find out in terms of VC and VR. That is our aim. So for that we have to do some equations. First of all, this 2d by n pulse width, 2d by n is equal to, here I have written pi by n minus 2x. What is this pi by n? See, this is total 90 degrees. Pi by n means pi by 2, which is nothing but 90 degrees. Pi by n minus non-conducting period. So this is x, this is x, which is nothing but pi by n minus 2x. Understand what I am saying? Pi by n minus 2x. Clear? Right? So here the conducting period only this one, that is nothing but pulse width. What about non-conducting period? This x as well as this. Therefore, I have written this total pi by n minus this non-conducting period, which is nothing but this one. Next, where x is defined the triangles shown in figures. What here we have to consider two triangles. See, the first one is this part. Okay, this part. So therefore, how can I write this equation? Means just so VC divided by pi by 2n. This part distance is how much? Pi by 2n. So VC by pi by 2n is equal to VR by x. What is VR by x means? You have to consider this part, this triangle only. Okay, this triangle. Okay, so from that, what happens? VR by x. This distance is x only, right? From this, what is x is nothing but pi by 2n into VR by VC. Substitute this equation in this first equation, then finally you will get this one. Therefore, what is pulse width 2d by n is equal to 1 minus VR by VC into pi by n. So in the problems, sometimes if you want to find out the pulse width, this equation is necessary. Okay. So now we'll go for this one problem we have to solve. So consider Vs is equal to 100 volts, Fc carrier frequency is 200 Hz, Fr is equal to 50 Hz, Vr is equal to 0.334 and Vc is equal to 1. Find the number of pulses represented in half cycle and find the RMS output voltage and fundamental component of output voltage. Here you please keep and find the harmonic factor HF3, HF5, HF7, HF9 and THD by using multiple pulse width modulation, right? So here, what is the first number of pulses? Formula is Fc by 2FR. We have already seen. Therefore, what is NB is nothing but FC 200 divided by 2 into 50, which is nothing but 2. And see, actually, we have derived this equation. And what is this equation is, in some textbooks, they are giving this equation by deriving some easy concept, but this is valid only for 2 pulses, that procedure. But when you are going for higher number of pulses, this procedure is not valid. So you please follow what I have given. So this is the better equation compared to this one. Just I want to show, in some textbooks they are following this one. Okay, right. But we have derived this one. Both we will get the same answer. But if you proceed my procedure, what I have given, each and every pulse we are deriving in the Fourier series, that will be better, giving the better result compared to this one. Okay, so that's why we are going for this equation only, right? So first we will find out the gamma, because in the equation we have to find out gamma also. So gamma is what the formula, pi by 2n. So gamma is equal to pi by 2n. 180 divided by what is n? We have discussed here 2, which is nothing but 45 degrees. Then what is the pulse width? So pulse width, just now we have derived the formula. 2d by n is equal to 1 minus Vr by Vc into pi by n. 2d by 2, n is equal to 2, right? 1 minus Vr. What is Vr? 0.334 divided by 1 into pi by n. N is nothing but this one. D is equal to 60 degrees. For the single pulse width modulation also, we have taken pulse width is 60 degrees D, and here also we are taking D is equal, getting D is equal to 60 degrees. Why? I will discuss, because it is easy to compare, right? When you take the equal pulse width, what is the advantage in single pulse and what is the advantage in multiple pulse, I will discuss, right? Now, this is your equation for harmonic, I mean to find out the peak value. Minus 8bs by n pi sin nd by 2 sin n pi by 2 cos n pi by 4 into cos of n into gamma plus 3 by 4. Just substitute 8 into 100. Okay, so bs is 100. Because of fundamental 1, here n value will become 1. So multiplied sin of nd by 2. What is n value? 1, right? D is nothing but 60 divided by 2, and sin pi by 2, and again cos pi by 4, right? So cos of what is gamma? Gamma is nothing but 45 degrees. 45 you can write it pi by 4 plus 3 pi by 4. So which is nothing but what happens? V01 P is equal to 90.06. This is the fundamental output voltage. Next, if you want to go for third harmonic, what happens? Just substitute, in place of n you just substitute 3. Okay, in place of n you just substitute 3. So a minus 8 into 100 by 3 pi into sine of, here you can substitute 3 into 60 by 2. Again here you can substitute sine 3 pi by 2 into cos 3 pi by 4 into cos of this one. Okay, and V03, I'm sorry, here you will get a plus here, it is not minus, just change it, it is a plus value, you will get it. Okay, I'm sorry for that. So we will find out the harmonic factor. Harmonic factor means what happens? V03 divided by V01. Therefore h of 3 is equal to what happens? 60.03 divided by, what is the fundamental we got? 90.06. So for that, what is happening? 66.6%. Similarly, you please find out for V05. Very simple, just wherever this n is there, you just substitute 5. For 7 means 7 you can substitute, and you will get this harmonic factors. And what is the RMS output voltage? Vrms is equal to Vs into square root of 2d by pi. You will get this one, which is same as that of your single pulse width modulation. And THD, Vrms square minus V01 square RMS divided by V01 square RMS. Therefore, what is the Vrms square? 81.60 square minus 90.06, 1.414 square divided by 90.06 divided by 1.414 square. THD how much? We are getting some around 80%. Okay, just 1 second. Yeah. Now what happens? This is the harmonic analysis for 2 pulse. So what we have, we got third harmonic 66, fifth harmonic is 20, seventh harmonic is 14.220, and ninth harmonic is 22.25. See, the first 3 are reducing, one by one it is reducing, and finally again it is increasing, right? And what is the THD? 80.39. What is the fundamental component? We got some 90.06, just small variation, but of course almost it is same. Now if you see comparison of single pulse width modulation and multiple pulse width modulation, two pulses. So here the formula is same, and V01 peak, see here 110.311, and here what happens? 90.00. This is the major disadvantage in multiple pulse width modulation. The fundamental component, if you observe this fundamental component, so magnitude is different, right? So nearly 20 to 20 volts, nearly 20 or 21 volts will be changed. So that is the problem in multiple pulse width modulation. The fundamental component is reducing. That is a disadvantage. So in single pulse width modulation, we have derived we have completed one problem, that is D. For D is equal to 60 degrees, the third harmonic is 0. Okay, but here the third harmonic is present. Right, what is that percentage? 66.6%. Next, if you take fifth harmonic, what is the fifth harmonic? This is the fifth harmonic, I mean V05B. What is the value? 22.06. Right, now here what is the value here? 18.02. Now see here the lower order harmonic, I mean this lower order harmonic voltage magnitude is little bit lesser than that of your single pulse width modulation. Here 22, here 18 we got. Similarly for 7, what happens? 15.75. Here what happens? 12.86. But what is the THDC? 30.06. Here 80.6. 80. Why this is 80 means here the third harmonic is 0, but here what is the third harmonic factor is 66.66. That is the reason, because of that one, so you are getting some TH will be increases. So here if one advantage is lower order harmonic voltage magnitudes less compared to single pulse width modulation, right? But what happens is the TH will be increases, right? So here what is the thing we have to go for? We have to tell it. If you go for multiple pulses, the lower order harmonics may reduces if you choose the proper pulse width. So if you are choosing the same pulse width, means the some harmonics will increases, some harmonics will decreases. So that is the some ambiguity presented in this multiple pulse width modulation. Generally, that's why generally nobody will use this multiple pulse width modulation. Everybody will goes for sine pulse width modulation. Okay. Now if we go for 4 pulses, this is the 4 pulses, right? So for this I have completed the derivation. So this one, this is the Bn, and if you go for each and every pulse, see, let us say the first one is gamma minus d by 4 to gamma plus d by 4. See here, gamma minus d by 4 to gamma plus d by 4, Vs sine omega. Next, for example, negative half cycle, if you take this one, once again, pi by 4 minus d by 4 to pi by 4 plus d by 4. This one, okay, Vs1. So this is negative half cycle, this is the positive half cycle. Right, see, I have derived the equation which is very complicated, right? So I want to show you. So because I don't want to go for each and every derivation. So nearly 6 pages are there. So see, this total derivation I have derived, right? I will give it to you, right? I will share this one. So each and every have completed, and one of my student also helped me to derive this equation, and finally we got this one. So this is the final equation: 2Vs by sine nd by 4 sine nd 1 minus cos n pi. This one, the same thing I have represented here. Okay, and this what I have written there. This is this one, and final equation is this one. So this is Vm sine omega t. Okay, so now if you go for the problem based on this, again the carrier frequency is changed, but the pulse width remains same, right? To understand what is happening, if you go for equal pulse width, what is NP? Fc by 2Fr. Fc is 400 divided by 2 into reference frequency is 50 Hz. Therefore NP is equal to 4. What is gamma is equal to pi by 2n. Therefore gamma is equal to pi into n value is 4. Therefore what happens? 22.5 degrees. Similarly, if you go for substitute the pulse width and will. See, while you are substituting this VR is whatever the magnitude is, that is a peak magnitude. Here, what is the formula we are using? That is peak only. Here VC also what we are getting, that is peak value only, how to substitute, right? So and pi by n. What is pi by n? Is nothing but value is 4, and we will get d is equal to 60 degrees. And this is the V01, the formula, and you please substitute n is equal to 1. What is Vs is equal to 100, and d is 60 by 4. See, d is 60 by 4. Gamma, what is gamma? 22.5. Like that, you please substitute, and you will get finally the answer. Okay, V01P is 86.025. Right. In case of two pulses, what is V01 peak? We got 90.06. Now see. Yeah. Now what is the fundamental voltage? 86.025. Again the voltage is reduced. This is a very important and drawback. So that's why generally we are not using this multiple pulse width modulation for practical cases, right? So this is the case. Next one, V03. If you take V03, what is this one? 32.43. What is the harmonic factor? 37.6. But previously for two pulses, what is the harmonic factor for 3? 66.6. Similarly, this one 30.75. And what is V07P? See, 53.32. In case of two pulse, V07 is 14.28. But here what happens? You are getting some 53.32. That is the disadvantage. You see, here it is reduced, but that compensationally somewhere it is increasing. Okay. So that is the problem in multiple pulse width modulation. If you choose same pulse width, if you change the pulse width, you may get some different values. Okay. So this is the your MATLAB THD, right? So this is fundamental 86.01. This is THD is increases 89.43. I didn't derive here in this problem, but you please try. Okay, we'll get the same whatever you getting, that result you will get. So if you substitute that formula, what is the formula I have given there for THD, just use it, right? And next coming to this here, see if you observe what the THD 89.43. So here the lower order harmonics are presented still, right? So due to this reason, if you having this THD means the filter size will be very high. For example, if you go for the sinusoidal PWM, in sinusoidal PWM, what is the reference wave? If you observe the reference wave, 1 second. Yeah, this is the reference wave. In sinusoidal PWM, that reference wave is sinusoidal. So when you are having sinusoidal means, what happens is the lower order harmonics are reduced. Here we are using a constant magnitude. So that's why still we are having lower order magnitudes are presented. So to overcome that problem, so it is better to use sine PWM rather than this multiple pulse width. Because of using constant reference value, lower order harmonics are presented still. So the filter size will be very high. In case of sine PWM, the THD will be 95% or 96%, but lower order harmonics are almost zero, but higher order harmonics are presented, which we can easily eliminated by using small filter. Here the filter is most important. So, but here because of higher order harmonics or lower order harmonics are presented, 3, 5, 7, the filter size is very high. So that's why we have to go for the next technique, the multiple, sinusoidal PWM technique. Okay, so now let me go for this MATLAB simulation for two pulses. So first I will run this simulation. Now see, this is the time values which I have kept, and these are the output values to generate the pulses. This is for positive, and what happens, this is for negative. Okay, right. So now if you observe the pulses, so 1 second. Yeah. So if you have the pulses, these are the pulses to generate the multiple PWM. So this is the pulses. So here, whenever your carrier wave is greater than reference, you will get this one. This is for positive half cycle. Okay. So because only this is positive, right? Next, right, we will go for negative half cycle. So negative half cycle. So in the negative half cycle, these are the pulses. Okay. So these are the pulses. So here it will be the negative. See, this is negative and we are getting this one. Okay. So this is about your this multiple pulse width modulation for second one. I mean two pulses. So we have to discuss with four pulses also. We have to discuss the four pulses also. Before going to the THD, how I have calculated this THD. So just 1 second. So this is the THD we have to observe. So this is the fundamental is 89.93, 90.06 we got, and these are the third harmonic, fifth and seventh. This is about your what we can say that two pulses, and we have to go for four pulses. We have to go for four pulses. This is the four pulses. So how can you generate these four pulses? You see, meanwhile, you please observe the RMS output voltage is this one. So 81.6, that is for two pulses or four pulses, you will get the same magnitude, right? Any case, if you derive, you will get the same thing. So now we'll stop here and we will go for the pulses, how we have generated the pulses, right? So this is for four pulses. So this is for the four pulses. See here for four pulses, you got what happens, four pulses. The same for the negative half cycle also, you will get the so negative half cycle you will get. This is about this one. And what about this total harmonic distortion? We'll see. Of course, I have shown already. The same thing we will get to this one. 37, 30, and 53. This is very important. This is increased. So that is the disadvantage. So because of these disadvantages we are getting, so generally we are not using this multiple pulse width modulation. So if you use different pulse width, if you choose proper pulse width, what happens is definitely you will reduce this lower order harmonics, right? But the pulse width is same for two pulse or four pulse, everything. So then what happens? You may not get lower order harmonics magnitudes are low. So this is about your multiple pulse width modulation. In the next class, we will go for very important topic, which is called as sinusoidal PWM. So here again I'm telling you, compared to the multiple pulse width modulation, single pulse width modulation is better in some extent. But if you choose the different pulses with a different pulse width, right, definitely the lower order harmonics will reduce. For two pulse I have shown clearly compared to the single pulse width modulation, but TH will be increasing. So that is the disadvantage. In the next class we will go for the sinusoidal PWM technique.